Imagine just for a moment cutting through the chaos of electromagnetic interference to create a clear, silent zone right where you need it most. China's new Storm Eye concept could, really make that possible, using synchronized drones to shield friendly systems while disrupting unwanted signals. In this video we'll explore how it works, why it's a breakthrough, and what it could mean for the future of precision signal control. Picture a scenario where two unmanned aerial platforms operate together, not to blanket an area with uncontrolled interference, but to sculpt radio waves into something highly precise. This is the foundation of the Storm Eye concept. It uses a pair of synchronized drones, each with a specific role. The first drone transmits a carefully calibrated interference signal. The second drone transmits a counter signal tuned to match the first in frequency, but opposite in phase. When these two signals meet at a precise point in space, they cancel each other out, creating what scientists call a null zone, a small pocket of electromagnetic quiet. According to the published research led by Professor Yang Zhan at the Beijing Institute of Technology, under simulated conditions, they were able to reduce interference at the friendly receiver to zero. This was not achieved by overwhelming power output, but through meticulous control of waveform, amplitude, phase, and timing. A 20 decibel interference to signal ratio, meaning the disruptive signal was 100 times stronger than the intended communication. The idea borrows heavily from advanced communication techniques like beamforming and phase cancellation, where multiple antennas work together to focus energy in specific directions or eliminate it in others. By adapting these methods for coordinated aerial platforms, Storm Eye could maintain friendly system performance in areas dense with electromagnetic activity, while selectively blocking unwanted transmissions. Conventional interference systems operate like a floodlight, powerful, broad, and honestly, pretty indiscriminate. For example, platforms like the EA-18G Growler or Russia's Kibini suite transmit across wide frequency bands, which can degrade both intended targets and friendly systems operating nearby. This broad brush approach can be effective for suppression, but sacrifices selectivity. Storm Eye introduces a completely different approach. Instead of saturating a space with uncontrolled signals, it acts more like a laser pointer, precise, targeted, and able to be shaped in real time. The synchronized drones do not simply transmit at the same target. One drone focuses on creating a controlled interference field, while the other crafts a matching counterwave to open up a narrow, interference-free channel for friendly use. The advantage is twofold. First, it dramatically reduces unintended effects on nearby systems that are not the intended focus. This is especially critical in environments where multiple units need uninterrupted communication or sensor access. Second, it is far more energy efficient. By only applying energy where it's needed, power demands drop, allowing for longer operational endurance and potentially smaller, lighter equipment. In technical terms, the principle is similar to beamforming, where antenna arrays control the phase and amplitude of individual elements to steer and shape a signal. In Storm Eye, the drones themselves act as the array elements, dynamically positioned in space to maximize the effect. So, at present, Storm Eye is a concept proven only in simulation. The results reported by Professor Yang Zhan's team are, honestly, pretty promising. In modeled scenarios with high interference to signal ratios, their approach achieved complete protection for the intended communication channel. Yet, translating this into real-world operations involves new challenges. Precise positioning of drones is absolutely critical. Even minor deviations in location, altitude, or orientation could disrupt the delicate phase relationship required for perfect cancellation. Environmental variables such as terrain reflections, atmospheric conditions, and unexpected movement patterns add layers of complexity too. In operational conditions, achieving and maintaining that precision would demand advanced navigation systems, rapid response control algorithms, and possibly AI-assisted coordination. If these challenges can be overcome, the potential applications are, significant. In complex operational environments, operators could deploy drone teams that shield their own systems while limiting others' communication or sensor performance. This would be particularly valuable in regions where navigation satellites are unavailable, or where multiple groups operate in overlapping ranges of the spectrum. Another potential application lies in protecting critical infrastructure or mobile command centers from disruptive interference while allowing their own communications to function normally. And beyond defense-related uses, similar technology could be adapted for civilian scenarios where secure, interference-free communication is vital, such as disaster relief operations or managing dense urban airspace with multiple drones. The Storm Eye concept represents a shift from broad, power-heavy interference to precise, targeted control of the electromagnetic environment. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries, and don't forget to leave a comment below. Thank you for watching, and see you next time.